In most courses at a college, your final exam is not going to change your grade. I've been doing this for a long time, and I've taught tens of thousands of students, and rarely is anybody's grade changed by their final. That's what we were just talking about. Your final would have to be otherworldly great, or the other thing, for it to actually move you out of whatever grade range you were already in, because the final is only worth a reasonable percentage, usually 20 to 25%. So if your final exam is rarely going to change your grade, then why do we get so stressed out over finals? In most classes I teach, every single person leaves the final with the exact same grade they had going in. The exception is the person who did really, really well, raise their grade. But it almost never happens that somebody drops their grade with a final. That is extremely rare in my classes. And again, I've taught, I don't know how many students I've taught, somewhere between 10 and 20,000 at least. And so I've given a lot of final exams. And generally speaking, everybody walks out with the same grade they had going in. And so what do we do to ourselves during finals? We are so stressed out. Do you realize how many people are sick during finals? In the December, it's worse. I would say between a fourth and a third of all the students sitting in the class have rotten colds and things, sniffling and snorting and chortling, pre-COVID, I mean, because they haven't slept, they haven't eaten, they haven't taken care of themselves because they're cramming and studying. For what end? I mean, the grades never changed anyway. And we do all of this self-inflicted torture. So that, look, if you just prepare and review and do your stuff, you're gonna be fine. Good morning, Robert. All right, so just have them. Hold on. Did I give yours to somebody else? No, they were going to auction off your points, I think. Not yet. Okay. So today, the topic we're starting these last 2 days is something called linear regression, which sounds kind of scary, but it's actually pretty simple. The concept. There's a lot of calculator buttons. Now, go back to baby algebra for a moment, okay? In baby algebra, if I gave you the equation of a line, could you graph the line and tell me points on the line? Think baby algebra for a moment. So if I said, y equals 2x plus 5, could you tell me ordered pairs on this line? Anybody? Yeah, I'm giving you a line. Could you tell me points that are on the line? If I gave you an x value, could you tell me the y value? So if I said, all right, I'm going to give you an x value of 2, what would the y value be? If I replace x with 2, what would the value of y be? Oh. Yeah, this is supposed to be the easiest thing you've ever done in your life. Yes. There's absolute, by the way, I couldn't make lines hard if I wanted to. Why? Because they're the easiest thing you ever learned in algebra. Plus, you did it in pre-algebra, you did it in elementary algebra, you did it in intermediate algebra. If you got pre-calculus, you did it in pre-calculus. Lines are the things you've done more than anything in your life. But if I give you the equation of a line, you could tell me points on the line. Let's say I give you a -1. What would the output be? Three. Now, in general, if I said, what does the line look like? You'd say, well, it has slope 2. Remember this? And the y-intercept is 0, 5. So it looks something like this. Okay. If I give you the equation of the line, you can tell me everything in the world about the line. You can tell me points on the line. Agreed? You can draw the line. That's easy. Regression is when you work backward. So regression would be, I didn't give you the equation of the line. I gave you information about the line, and you told me the equation. Oh, okay, so that's a little bit more complicated. So in that sense, that would be more like I said, I'm thinking of a line, and my line passes through the points 2, 1, and 4, let's say 7. And I want the equation of the line. I want other points on the line. I'd like the graph of the line. Well, that's not as easy, is it? Because I didn't give you the equation. Okay, so what sort of stuff could you do in this case? Well, you could draw it. So 2, 1, 4, 7, I could draw it and try to come up with an accurate line. I could come up with the equation of the line by using formulas that we know from algebra, point slope formula, you know. But if I gave you points on the line, coming up with the equation of the line is just a little bit more taxing, isn't it? I got to work a little bit harder. Okay. So regression is you're given information about the line, you're given points, and you're asked for an equation. Now, one of the nice things about lines in general is if I give you 2 points, okay, you guys are all looking somewhere else. Maybe put the phones down for a minute. I'm only going to explain this once. Okay. We're going to do one problem. I explain it once, and this is a question on the final. You probably want to get it right. All right. Yeah, there were things that people missed on the last exam, which I can't believe anybody would miss because it was the same problem on the practice test, and you did the same problem on the quiz twice, most of you, and then you do it on the exam and miss it. That's not good. That means the retention is not there. Yeah, you got to retain things. You know. So if I give you exactly 2 points, how many lines can I draw through them? If I give you exactly 2 points. 1 line. That's one of those age-old things, you know, through 2 distinct points, there's only 1 line. Now here's the thing. What if I gave you a bunch of points? Now here's where it gets tricky. What if I give you a bunch of points? Because there's information, I'll tell you where the points come from. I'm going to give you a bunch of points. This is sometimes referred to as a scatter plot, what I'm doing. I've got a bunch of input outputs. It could be whatever you want it to be. We'll set up scenarios. I gave you a bunch of points. Is there one line that passes through all of those points? Think of kind of like a pinball, right? Is there one line that passes through all of them? No. The moment I gave you a third point, there was not one line, was there? Does that make sense? Yeah. So then the next question would be, okay, there's no line that passes through all of them. But is there a line that is closest to all of them? Ah, Lila's raising, she's nodding her head. And just, would you say it's probably something like that line? Is that reasonable? There is a best line. This line is sometimes referred to as the line of best fit. It's more formally called the least squares regression line. That sounds scary. I like line of best fit. There's an infinite number of lines I could draw. I could just draw them randomly all over the place. But we agree that there is a best line. There's a line that is closest to all of them. And statistically speaking, when you're gathering data, you're never going to have things all line on the same line. That just can't happen. So there's always a best line. So the equation of this line is next day's lecture. Today's lecture is about something called correlation. In simple English, correlation is basically how close are my points to the line? Not how good is the line. No, there's only one line. There's actually a formula for finding that line. There's an absolute mathematical formula. We're going to learn it. The question is how good is the line? See, if my orange points are going every which way, would you say they're not very close to the line? Do you think that's reasonable? But what if my orange points actually, here's my orange points now. Would you say now that, the points are actually pretty close to the line? The closer my points are to the line, then we say the more correlation there is, the higher the correlation. The further my points are from the line, the less correlation. Well, why is that important? Because if I have data and I can produce this line, then you can ask the question, well, I have another input. I'm going to give you an input. Can you tell me what the output is likely to be? In other words, what would the output on the line be? And that's what we do in real life. If I give you more input. Now, let me give you some simple examples. This could be every year your company made a certain amount of money. Okay, let me give you a really simple example because we're going to do things like this. Your company's been in business a long time. Okay, and it doesn't matter when we start. We can say the x-axis is the year. We could say the company started in the year 2000. Okay, so let's call 2000 0, and then 2001 we'll call 1, 2002 we'll call. Does that make sense? We'll call that, and then the y-axis will be how much money your company made. So as I'm moving down the line, and I'm charting the growth of my company, and this year my company made this much, and this year we 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 made this much. And what you notice is, the growth is fairly steady, and it kind of looks linear, doesn't it? It's not curving all over the map. Does this make sense? So the question is, based on this model, we agree there is a line. And I don't know what the line is yet, but maybe the line probably looks something like this. I've gotten to this year. Could you basically predict what next year will be? Realistically, in other words, can I use the line to predict what we believe next year will probably produce? Yeah, this is what's actually done in real life. If we have essentially linear growth, then it's reasonable to say, well, next year, there's no reason to think it's going to change. So next year, I can predict what I think it's going to be. Now, in real life, we'd put a plus or minus on that, wouldn't we? We put a cushion just to be safe. Oh, now, correlation is not the line. Correlation is how close are the points to the line. Now, a correlation, the population variable for correlation is the Greek letter rho, R-O-H. And it kind of looks like a curvy P, but the funny thing is, it's the Greek R. Yeah, the Greeks couldn't make their rhymes. But what is mu? That's the Greek M, right? And that's got a little tail. What's the sigma? That's the Greek S. Yeah, the Greeks had different symbols for their letters. Rho is that. So remember how we've done things all semester. The population variable is the Greek letter, mu, sigma, chi-square. The statistic, what we're actually going to measure with a sample, R. So you don't have to worry about making really good rows. So X bar is to mu, as S is to sigma, as R is to rho. Rho is the actual population correlation, which you can't know because that would mean you'd have all the data on planet Earth. Agreed? You can never have the population realistically. So you collect the sample, you calculate that value, rho. R, sorry. Now, R is a number always between -1 and 1. -1 or +1 represent perfect correlation. That would mean every point is on the line. R of 0 means absolutely no correlation whatsoever. It's absolute randomness. And I'll show you what I mean. You say, well, why would -1 be good? Oh, that's actually easy. This would be an R, in my picture, would be an R very close to 1. It'd probably be like 0.9 or something. What do you think an R of -1 would look like? Want to take a guess? Oh, if they're going downhill. So if the points are going uphill with a positive slope, R means they're perfectly fitting the line. If the points are going downhill with a negative slope, R of -1 means they perfectly fit the line. But remember what that would mean. If they're going downhill, that means the bigger the input, the smaller the output. If they're going uphill, the bigger the input, the bigger the output. So an R of +1 just means you have a positive slope and the points are perfectly on the line. It does not mean the slope is 1. It has nothing to do with the value of the slope. It just means it's uphill. If the R is -1, then it's going downhill and the points are perfectly fitting. What would an R of 0 be? Here are my points. All right, can you tell me the line of best fit? My points are kind of in a circle. There really isn't going to be a line, is there? They just, do you agree that this is worthless right here? If my points formed a perfect circle or a perfect polygon in general, there's no correlation whatsoever. Okay, now here's one of the problems of correlation that we have. There's a lot of situations in real life where there really isn't correlation, but when I look at a picture, it appears there is. And here's what I mean by that. Okay, I'm going to put Velcro on the wall here. And you're going to take a bunch of those, little fuzzy things that stick to the Velcro. I don't know what you call them, maybe little fuzzy balls, like when you were kids. Okay, you got it? So Robert's got a handful of them. He's got 20 of them in his hand. And he's going to stand back and he's just going to throw them at the wall. Got it? He's just going to throw them at the wall. Are they going to land in a perfect circle? No, that would be actually impossible. So in other words, they're going to land kind of going uphill or they're going to land kind of going downhill. There's going to be a picture created when Robert throws all of his little fuzzy balls at the Velcro. You got it? But when you look at that picture, it's going to give you the illusion that there's a line there, because it would be impossible for him to throw those things and have them make a perfect circle. Understand, the perfect circle would be impossible. Oh, so no matter what you did, it would give the illusion that there might be correlation. In other words, he'd have a path maybe that looked like this, or a path that maybe looked like this. If I said, Lila, I want you to take 3 darts, and I want you to throw them at the board. Or, okay, we're going to put a dart on it, so I don't want you to hit it from the board. You're going to throw 3 darts at the board, okay? And 1 dart hits here, 1 dart hits here, 1 dart hits here. Agreed? That's reasonable. You know what? There is clearly a line of best fit. But would you say there's any correlation? No, you just threw 3 darts at the wall. There's no input output. There's no cause and effect. But you threw 3 darts at the wall, but there's still going to be a line of best fit. There's always going, oh, okay. So here's the first thing we always discuss. We actually have to decide, is there actually correlation? Is there a reason to even study these things? If I just randomly threw points out there, it would give the illusion that there was correlation when there may not be any. There are many historical precedents for this. One of my favorite ones, and we studied this when I was in school. I don't remember the exact year. I know it was in the 70s and 80s. They did this study in New England. And they compared ice cream sales to shark attacks. Now, this was in New England, in coastal towns in New England. And it's a very famous study. You can look it up. It's awesome. So a cause and effect would be, the cause would be the input, the effect would be the output. It'd be kind of like saying, and we're going to use this a little bit later, alcohol. Okay, we talked about this, right? That a lot of colleges will actually take volunteers to do the alcohol studies. So they sit there and they say, okay, consume a drink now. And then they give you, the little red light buzzer, and then you click the bell, and they're comparing reaction time. This is done, by the way, all the time. That's why on your driver's license, you see all those little charts about alcohol and body weight and time. They've studied many, many people, and they take volunteers often at colleges. And so you have a drink, and then you react to the stimulus, and based on your reaction time, they'll say, okay, the alcohol is affecting you. And then we do this over several hours. There's a cause and effect. The alcohol is the input. The effect is your reaction time. And we know that the more alcohol you consume, the slower your reaction time. So there would be a positive correlation: increase alcohol, increase reaction time. It would be unreasonable to say the more alcohol, the faster you get. No, I don't think that would happen. Do you agree? That's probably not. So that would be a positive correlation, because as one goes up, so does the other. There's a clear cause and effect. That's important. I believe you don't say reaction time is causing you to drink. No, the drinking is causing a change in your reaction time. Clearly, the alcohol would be the independent variable, the input. The reaction time would be the output. So in the study in New England, they said, okay, as ice cream sales go up, shark attacks go up. And as ice cream sales go down, shark attacks go down. And the correlation was very strong. So does that mean that so if you go out today and you buy an ice cream cone, that you're in trouble? You're gonna, one of those land sharks might even get you, when you're at Walmart later on or something. Now, do you believe that ice cream sales cause shark attacks? Do you think there's how in the world could ice cream sales have such a high correlation? They're the input. Is there a cause and effect? What do you think?
I mean, I guess that even in the most similar circumstances, correlation is not causation.
That is the whole point. This is where we have to step back and say, do I believe there's a cause and effect here? That's what you're saying. Sometimes there's something called a confounding variable. There's a third variable involved that we're not considering. Do you know what it is? It said New England. Weather. When do shark attacks happen? When people are in the water. In New England, when are you in the water? Only in the summertime, pretty much. By the way, when are you more likely to buy ice cream? When you're out and about and it's hot. During shark attack. In other words, it sounds funny, but the weather dictated ice cream sales going up, because when it's hotter, people eat ice cream. When it's cold and freezing and snowing outside, people aren't consuming a lot of ice cream. They're consuming warm things typically. In the summertime in New England, people consume significantly more ice cream. And in the summertime, they're going in the water. Therefore, there will be shark attacks. Is the ice cream causing the shark attacks? No, the weather is causing people to go in the water, and therefore, so in other words, that's called the confounding variable. There is no cause and effect. Ice cream does not cause shark attacks. But like I said, if I was plotting the points, it would certainly give the illusion that there's a cause and effect. So what we do in statistics, first of all, we determine, do we even believe there's a cause and effect? One of the things I remember when I was in school, and even in high school studying, I always found this one really, really funny. I don't know if it's still true, but I know it was true for the second half of the 20th century, literally from World War II on. If you followed the stock market, I always get the term wrong. The length of a woman's skirt, is that called the hemline? Like, how high up or down it is on your, I don't own any skirts. I think that's called the hemline. I think that's what it's called. So fashion designers typically will design things not for next week, but for next year or even 2 years down the road. They'll design things for way in the future, and then they'll come out and they'll sell them because they have to make them all first. And so what they found was I remember there was a 50-year period that they studied that as the hemlines went up and down, the stock market followed almost an identical pattern, it was uncanny how close. If you followed the stock market, up and down trends, and you looked at the hemline, but the hemlines came before the stock market behavior. So very clearly the hemline was causing stock market behavior. So when the hemlines were up, the stock market was up. When the hemlines went down. Now, do you think hemlines are causing the stock market to go well? Do you think the people doing stocks have any idea what the hemlines are going to be next year? No, but there was an unbelievable strong relationship, but is there a cause and effect there? The intelligent person would say no. So in other words, we have no reason to believe there's a cause and effect. So we're not going to sit there and do the mathematics of that. Where would there be a cause and effect? Well, for example, I said alcohol consumption, reaction time. I have a very simple one though that I've actually looked at, and I've done very loosely for final exams. I will ask people, there's two things. I'll ask people going in the final, please keep track of how much time you prepared for the final exam. And I mean, be honest, and I've done this for semesters. So everybody gives me a number. Maybe it was 2 hours, maybe it was 20 hours, maybe it was 15 hours. And then I would look at their performance, usually based on the rest of the course, not based on everybody else. So what I found was the higher the number of hours of preparation, tell me about the performance. Which way did it probably go, up or down? Probably went up. And I found there was a pretty strong correlation. Another one I did, I had a class once where, because it was a once a week class, I don't like once a week classes. It was a once a week Friday night class, 6 to 9 p.m. Can you imagine? Oh, we did those for years and years. They were very popular. You worked all week, your full-time job. You came to Mesa and took a night class and tried not to die by 9 o'clock because you were so exhausted. But I taught this class, I just gave a midterm and a final. And what I found was the higher the midterm performance, typically the higher the final performance and vice versa. Very strong correlation there. Does that seem reasonable to you that there would be a very strong correlation? Yeah, so that's an easy one to study because you already believe it's reasonable to assume there's a cause and effect, right? So prep time, good test results, that makes sense. By the way, there's another one that is often studied. I don't do it because it's too much work, because it requires too much work for everyone else. And it's not study time. What do you think it is? Sleeping time. Sleeping time versus performance.
I do a lot of that.
But think about that logically. Do you agree that if you charted your sleep over a long period of time, when you get less sleep, your performance probably goes down? When you've got what you consider enough sleep, your performance is probably better. I don't want to say, okay, well, then if I sleep all day tomorrow, I'll get an A on my test. No, I don't mean that. It's usually the other way. Less sleep, less performance. But again, that would be a correlation there, we believe. Question?
So would you say that it would also be somewhat causational if we were also to measure like a person's work hours as well?
It could be. Yeah. There are a lot of, and it's kind of a common sense argument. You say, yeah, I think there's a lot of areas out there where I think one thing has a strong influence on the other thing, but it's only worth studying from our standpoint if we believe it's a linear relation, not a big curve, not a parabola or an exponent. If we believe it's a linear effect. Now, in the higher levels, they do stuff with logarithms and exponentials. It can get kind of crazy, because if it looks exponential and I take the natural log, it might make it linear. That's called log linear. We study that in the graduate level. But let's just talk about something we believe is linear. So I'm going to show you how. So here's the thing. You're not even going to do the problem. You're not even going to take on the problem unless you already believe it is reasonable that there's a cause and effect, right? Ice cream sales and shark attacks, we don't believe that's reasonable. There's a cause and effect, right? Hemlines and stock market performance, we don't believe there's a cause and effect. That's just pure coincidence. Now, realistically, there's probably a third variable, like the weather in the case of New England. Okay, that's why I always love it, because people point, it is New England. I've known people from New England. My wife was born in Connecticut. You don't go in the ocean like you do in San Diego. We go in the ocean in January in San Diego. You may not go in the ocean until July in New England. June might still be too cold. So we go, oh yeah, I didn't really think of it that way. Okay. So I have a set of ordered pairs called X1, Y1, X2, Y2. That just means first point, second point. How many of them? Well, N, Xn, Yn. I have a set of ordered pairs. It's called my data points. It's probably a good idea to plot them on an XY plane. And we're going to only use a few. Okay. A true scatter plot problem, I might have hundreds of points. Heck, I could have a couple of thousand. No, I'm not going to sit there and do that by hand. For our class, I might give you 5 or 6 points, right? Everybody understand? So we're going to plot these points wherever they stand. Next day, we're going to look at how to calculate the line of best fit. Today, I just want to be able to calculate the correlation, if there is any. Hold on. I brought you some, hold on, where did I put it? I printed some, there's one more additional page of the formulas, by the way. I figure out what I did with it. I just printed it right before class. Oh, here we go. Here we go. All right. I'm gonna write everything down, but it's on here. There are a lot of formulas on here. We're not. Did I get this before?
Yeah.
Oh, this is the 4th page. You got one?
It's this one, right?
Yeah. Yes. Let me give you this one, because this is sort of. Well, no, it's looks like it's different format. Let's use this one. Yeah. Okay, so I'm going to show you where this stuff is. Now, you see right now this is linear correlation / regression. Correlation, you see the formula, there's R. There's a formula right there. R equals SSXY over the square root of S. That looks really confusing and crazy. Well, there's 3 things there that I'm going to calculate, and they're actually very simple to calculate. But you have to calculate them one at a time. And what happens is I'm going to get a numerical value for correlation that's between -1 and 1. Now, here's the thing. How do I know if correlation is strong or if it's weak? Well, if my correlation is negative, that's not bad. It just means I'm going downhill. So what we actually usually do is we don't look at the value of R as much as we look at the value of R squared. Okay, so if R squared is small, remember, if you square a small number, if I square a half, I get a 4th. When you square a small number, it gets smaller, doesn't it? If I square a 1/3, I get a 9th. So if R is already between -1 and 1 and I square it, it's going to get smaller, but it's going to remain positive now if I square it. So usually we say we like R squared to be at least a certain size, maybe 0.5, 0.6, 0.7. Okay, because that way, whether it's positive or negative, it didn't matter. So I'm going to show you how to calculate. Now, there's a couple of things going on. Now, we know what variation is. Okay, so what I want you to do before we start the problem, there's a few things that we're always going to calculate right at the beginning. We're going to calculate the sum of the x's. We're going to calculate, write them all down, the sum of the x squareds, the sum of the y's, the sum of the y squareds, and the sum of the products of x and y. There are 5 things that we need to calculate. So what is the first one? That's just x1 plus x2 plus x3 plus x4. And add up all the x's. What's the sum of the y's? Same thing, add up all the y's. What's the sum of the x squareds? We needed that for variance. Oh, that would be this guy squared plus this guy squared plus all the way down to here. What's the sum of the y squareds? Same thing, this guy squared plus this guy squared plus all the way down to here. Right, we've done this a million times. We did those at the beginning of the course. What's the sum of the xy's, do you think? This times this plus this times this plus all the way down to here. Okay, you with me? That's what we need. So let's do an example. I'm going to give you some points right now. So let's say my points are -3, 2, and then -1, 5, and then +2, 8, and then +4, 16, and then 7, 21. I'm going to give you 5 data points. And I would like you to calculate each of these things. So -3 plus -1 plus 2 plus 4 plus 7, that would be the sum of my x's. Okay, let's do that. Take a moment and tell me what each one is. By all means, use your calculator.
And then xy is just 3 times 2 plus negative 1 plus 2 times 8.
Sorry, do we have all of them yet? Just write them right under. Anybody have the sum of the x's yet?
9.
So 9. I'll do these ones. The sum of the y's. 52. All right. Go a little bit slower than the sum of the x squareds. Not quite.
I got 78.
So 10, 14, 30. How about 79? Double checking. Did you get 79?
I got 78. And I put that in the calculator.
9 plus 1 plus 4 plus 16 plus 49. $59?
I got 59.
Okay, you guys are not squaring. You can't do this. That equals -9. How do you square a negative number?
Then that's what I did.
Okay.
Yeah, there's an unforgivable error, and that is squaring a negative number and getting a negative value. No, you got to put parentheses around it. Yeah, that's why you got 59, because you subtracted that and added. So at some point, tell me that you got something else. You haven't got my number yet.
79.
Ah, okay, finally, Robert agrees with me. Okay. I usually refer to Robert, he's the sage. He's the calculator guru. Okay, how about the y squareds? That's gonna be much bigger. So 790? I believe that's correct. This is not hard. You have to be careful. I said it was going to be tedious calculations. Okay, we just got to be careful. I was slow. And then the last one is you're multiplying each one here. So this would be -3 times 2. So -6 plus, -5 plus, 16 plus, 64 plus, 147.
And that's gonna be mine now. Sorry, I'm going.
Oh, you got, okay, good. At some point, we want to know that we can do all this. Okay, what do we get for the last one, anyone? $216, good. All right, these are numbers we're now going to use in all of our calculations that we have to perform. But this is sort of like, at the start of every problem, you always do this. Now, let's suppose you had a lot of points. Would you be doing this with a calculator?
I'm sorry. How did you get? What did you do again?
That product plus that product plus that product plus that.
You multiplied them?
Yes.
Oh.
I have said that a couple of times. Sure. X times Y. So this one's odd. We've never done that before. It's the product. So I'm taking the product of each of those and then adding them all up. Now, let's suppose you had 100 points. You have 1,000 points. Are you going to do this with a calculator? Oh, heck no. Because we're going to make mistakes and it's really slow. So what you do in that case is you just have the input into the computer and you'd ask the computer to add up the X's, add up the Y's and do all that. Agreed? Nobody would be doing this by hand if it was big. We're only doing it by hand because it's small, so we understand where the numbers go. Understand in real life, when you're using a computer to do big problems, you have to know how to do the problem by hand. Otherwise, you won't recognize your answers and what they mean. Because is it possible your answer is incorrect, even with a computer? Yeah, it was entered incorrectly. Remember, we've talked about outliers and things like that. I know what the answer is supposed to look like. If I have a large data set, I'm not going to do it by hand. It would take forever. But I still have to understand the pieces of the puzzle so that I can recognize what an answer looks like and where everything goes. Now, I have all this information. Let me erase this. Now what we're going to do, when you compute variance, what is the formula that we always use for variance, for a sample? Do you remember? S squared, it's on your thing, was the sum of the x squareds minus n times x bar squared over n minus 1. Okay. But where did it actually come from? So if we go backwards, the actual formal definition is each score minus the mean quantity squared over n minus 1. Do you remember that? That's actually how we started it. And then I multiplied it out. This is a shortcut. This is the actual formal. This is significantly easier and faster. Okay. But what is this? This is a sum of a bunch of squared scores, technically, because I take a difference and I square it. I take a difference and I square it. This is much faster. So the numerator is the sum of the squared stuff. And then you're dividing by n minus 1. The numerator here, that part right there, I'm giving it a new name. I'm going to call that the sum of the squares of x. That's what the SS stands for, the sum of the squares. Oh, now, do we have all that information right here? Almost. What don't I have yet? I don't have x bar yet. What would x bar be? If the sum of the x's is 9, and how many points are there? 5, that would be my n. What would x bar be? Wouldn't it just be 9 over 5? Oh, so is x bar an easy thing?
Yeah. Yeah,
x bar is easy. X bar is about as easy as it gets. Can you tell me y bar? Yeah, it'd be this over 5. Ah, you with me so far? So for this problem here, my SSX would be, well, actually, let's go ahead and say, what is X? Let's write it down. What is X bar? You said it was 9/5. And by the way, if that is a terminating decimal, and always use the terminating decimal, it's just easier to enter. We know fractions are always correct to enter our calculators, but when there's a lot of calculations, sometimes it takes a while and I got to use extra parentheses and yada, yada, yada. So that's a terminating decimal. So that means 1.8. What's Y bar? We just said that's 52/5, and that's what? 10.4. You with me so far? So SSX is, okay, according to my formula, what is SSX? Okay, look at your sheet. It says right there, SSX is the sum of the squareds minus n times x bar squared. Hey, it's exactly the numerator of variance. Yeah, that's what I was just saying. It's exactly the numerator of the variance. So it would be this guy minus the n was 5. My x bar was 1.8, and I want to square that. So exactly what is that going to be? And I don't do any rounding here. So exactly what is this going to give me? Anybody? I get 62.8. Okay, Robert, our minds are becoming one, which is kind of scary. I know. You're gonna start dressing like me, so, solid colors. Everybody okay with that? Now we have something called SSY. If the sum squares of the x's is this, what do you think SSY would be? Well, let's take the exact same formula, but replace x with y. Oh, so that would be the sum of the y squares minus n y bar squared. Right? The sum squares of the x's. So it'd be kind of like me asking you to find the variance of the y values. There's nothing wrong with that, by the way. I can find variance of other things. So if I wanted to find the variance of the y values, then I would just do that. Okay, so what's SSY? Sum squares of y would be the 790 minus 5 times what? The square of 10.4. Let's calculate what that is. Again, in real life, you'd have a lot more than 5 points. We don't need more than 5 points to figure out what we're doing here, though. $249.2. Now there's one more calculation, and that's the sum squares of the xy's. Now, how do we find the sum squares of the xy's? What do you think? Well, it's actually fairly simple. Technically, isn't this y bar times y bar squared? And in the sum squares of the x's, it's actually x bar. I want the sum squares of the xy's. Well, obviously, this is x times x, or excuse me, y times y. The other one was x times x, so this would obviously be the sum of the xy's, x times y. Minus n times, what do you think? If the sum squares of the x's was x bar, if the sum squares of the y's was technically y bar, then the sum squares of the xy's ought to be perfect. Does that make sense? Do you see the consistency there? Ah, okay. So the sum of x times x's, the sum of y times y's, and now it's the sum of x times y's. So that's this guy. So I'll write right here so I can fit it there. So that's going to be 216 minus 5 times 1.8 times 10.4. What was that? I got something slightly different.
Oh, I put 210.
Is that 192.4?
Yeah, I got that. So the mind link is now switched. Sorry, Robert. Me and Andrea are now on the same wavelength.
Sure.
Okay, these are the numbers. These are the only numbers that I need to now perform my overall calculation. So we're going to put these in our back pocket, and I'm going to leave these up here. Now I'm going to move on, and we're going to come back to them. So let me erase. Also, what I want to do is I'm going to draw a picture. I'm going to draw a picture. You know, it's going to be a loose picture, but I want to draw a picture that represents the ordered pairs. Okay. So the x's are going to go from -3. I'll do the best I can for accuracy. 1, 2, 3, 4, 5, 6, 7. Probably overkill. The y's are going to go from, looks like 2 up to 21. So 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, I want some accuracy here. 1, 2, 3, 4, 5. I want to plot these 5 points just so we can kind of get a loose idea of how well they fit on a line. Does that make sense? Because if I plot these 5 points and they kind of look circular, we expect basically no correlation. But if I draw them, they look fairly tight, then we would expect a very strong correlation. Strong meaning close to 1 or close to -1, we would calculate it. So -3, comma 2. -1, comma 5, right there. 2, comma 8, about right there. Having graph paper makes it a little easier, by the way. 4, comma 16, there. And then 7, comma 21, about there. Now, see these points? Are they all on the same line? No. But do they kind of fairly line up? That's really the thing. Do they kind of fairly line up to you? Yeah. Which means that if I was able to figure out the line of best fit, I don't know what it is. That's next day's lecture. But if I was able to kind of loosely draw a line, you know, maybe my line is something like this. Actually, that's pretty darn good. I usually I can do circles. I can't do lines very well. Would you say now, looking at that all of these points are really close to the line? By the way, none of the points are on the line. That's an interesting thing. The line of best fit, none of the points are ever on the line. We just like them all to be close. So because all of my points appear to be pretty close to the line, we would say we believe the correlation is going to be high, a number close to 1 or -1, which is my correlation going to be close to 1 or -1? Because it's going uphill. It's that simple. Oh, if it was going downhill and it looked like this, then we'd say close to -1. It's important to realize positive slope, positive correlation, negative slope, negative correlation. Correlation is not the slope. Correlation is how close are the points to the line. It doesn't matter how steep the line is. It's just how close are the points. Okay. So I believe we're going to get a really strong correlation. So those viewing at home, let me, oops, sorry. That's an illustration of our line. It's roughly, roughly accurate. It's not going to be perfect. I'll do my best to freehand the line. But, all right. So now what we want to do is actually calculate. Now I said there's a statement that says R squared gives you kind of the explained. In real life, let's say there was, 1 million data points in real life. And let's say we actually had all of them and we had a powerful computer, we could actually calculate exactly what the correlation is. Well, it'd be good. I wouldn't need to do an experiment. I wouldn't need to do a sample. I wouldn't need any of this. But since that isn't the case, when we do our calculation, R squared kind of gives us an idea of how good we are. And the closer R squared is to 1, the better. So that statement where it says explain variation over total variation, that's what the R squared is. The closer that number is to 1, what we see is called the explained variation, and what it actually is the total variation. That's an idea. You're never going to actually try to figure out what the population is. You're just saying, oh, okay. So if my R squared is not a very big number, then it means I have a lot of randomness and I can't tell you, I can't tell you a really good conclusion. We really like situations where it's close to 1 or -1. Now, remember, we said you're never even going to start the problem unless you had reason to believe. I like the word Lila, causation. Unless you truly believe there really is a cause and effect. And I gave you several examples where you'd say, yeah, study time and exam performance. That seems like that's a pretty obvious causation, right? The more you study, the higher your performance ought to be. How about in athletics? Could you equate practice time and performance, perhaps? Do you think that would be a reasonable thing? Now, is it going to go up forever? Or do you think it'll level out at some point? In fact, in athletics, could you go up and even come back down? Yeah, what's that called? Overtraining. Yeah. So by the way, it's a finite interval in real life that says you can't do this forever. Okay, that's kind of the idea. For little is good, then a lot is great. Well, maybe only up to a point though. I can have improvement to a point and then I might drop off. But in a lot of situations, we can actually look at this. In the NFL, I love football. They do a lot of this and people don't realize a lot of this is how the betting occurs. They call it trends. You ever heard that term in sports? When they talk about trends. Trends, if I see a trend, then what I do is I try to extend it and say, what do I believe is going to happen if that trend continues? Now, I always laugh when I'm watching a game and it's early on in the game. Let's say we're in the first quarter of an NBA game and the team has, 10 points 2 minutes in. I mean, that happens. And then they'll say, well, at this pace, they're going to end the game with 240 points. That would be correct, by the way. Are they going to have 240 points at the end of the game? No. What they're trying to do is say, here's what they did over 2 minutes. Let's extend that for the rest of the game. Yeah, they scored 5 points per minute. There's 48 minutes in a game. You can't automatically assume it's going to continue. They may not score now for the next 5 minutes. Agreed? So there are times when it's not reasonable to automatically just extend it. So it's like you said, well, if I work out 2 hours a day, I'll have this great performance. So if I work out 24 hours a day, no, it probably isn't going to work, is it? So it's not an automatic thing that if you see a correlation that it extends forever. Really what correlation is, if I have a correlation over an interval, then anything in the interval, I can use the line. I can't always use the line for later. And I'm going to give you an example of this. Investments. This is one of the really dangerous things. And you'll see commercials for investments all the time. And they'll say, last year or last month or last week, we performed like this. We did, this great. So therefore, for the next 10 years, no, you can't even say what's going to happen in the next 10 minutes. That's called predicting the future. If something did really well in recent history, then it's reasonable to say, it ought to do really well for a short period of time. But does that mean it's going to do really well for eternity? You can't even say what's going to happen tomorrow. So that's where sometimes it's kind of iffy in the advertising. And then, by the way, if you ever watch those commercials, the financial commercials, they'll usually throw in a statement like, past performance is no guarantee of future. You ever heard lines like that? They have to say that because otherwise they're lying to you. Past performance does not mean, that'd be kind of like saying the football team just had a great game last week, therefore they're going to win all the rest of their games. No, I don't think it works that way. You still got to do it. I got an A on my last test, therefore I'm going to get an A on all the rest of the tests. Really? Is that how it works? Okay. Yeah. So it's only within a finite interval that we can actually use the predicting part of it. So what we want to do now is we're going to do the calculation for the R. Okay. But also we want to do a hypothesis test. So here's how it works. It's a strange hypothesis. I believe there is correlation, and I'm not going to go forward unless I can prove this correlation. So the null hypothesis is that there's no correlation. And you let the data tell you otherwise. Okay, so if I start by assuming, we're going to assume there's no correlation, and then when we do the calculation, if the calculation is overwhelmingly obvious that there's correlation, we will say, okay, there's correlation. But if the calculation is so weak that you go, you know what? My points kind of lined up on a circle. I'm going to get my calculation is going to be really, really close to zero. Does that make sense? So the null and alternative is almost the same, and it's kind of an odd one. You say, I think I've got everything that I need. I'm going to go ahead and erase this. This is a kind of an odd one because of the way we set it up. We always make the null and alternative the same. That it's no correlation versus there is correlation. So the null hypothesis would be, now what was the variable we used for the population? Do you remember? The Greek letter rho. Our null hypothesis is there's no correlation for the population. Our alternative hypothesis, therefore, would be there is correlation, that rho is not zero. It's not whether it's positive or negative, it's just zero or not zero. Now, let's test at the alpha equal 0.05 level, okay? Therefore, I will reject the null hypothesis if, now before we start the problem, we always say it this way, zero or not zero. So it's technically a two-tailed test, agreed? So if what? If Z is bigger than something or Z is smaller than something. Oops, smaller than something. What's our magic number? Two-tailed 1.96, good. So if I'm bigger than 1.96 or more negative than negative 1.96. So we're the extremes. By the way, you would set up the null and alternative after you collect all the data and do all the calculations? No. You set up the null and alternative before you collect any data. Remember, you can't make the hypothesis fit the data. The data has to confirm the hypothesis. Everybody agree? It's got to be a little other way around. So in reality, you did this before you collected any information. But remember, it's because we had reason to believe that we thought there is correlation. Therefore, we're going forward with this. We could be wrong. It could turn out there really isn't any correlation. It's the illusion, like I said, when you threw darts against the board and they kind of gave the appearance that they lined up, but they're really, they look like they lined up, but that doesn't mean there's correlation. Okay, so that's why we always do it in this order. So now we're going to calculate the R. Okay. We calculate the R before we calculate the Z, by the way. So the R calculation is, let me make sure I write it down quickly. The R calculation is the sum squared of the XY's over the square root of the sum squares of the X's over the sum squares of the Y's. Now, what's interesting is these are basically standard deviations that we're taking quotients of. They're versions of standard deviations, strangely enough. Well, do we have all the numbers right in front of us? Yes. So let's put them in. So the first one would be, so my numerator would be 122.4. My denominator is the square root of 62.8 times the square root of 249.2. I have a product of square roots in my denominator, so it'd be wise if I use my parentheses well. I've got extra calculators if you have one you don't trust. Now let's all see what we get. 122. You are fast, Lila. I'm not that fast. So you got point. That's what I got. Now, you're going to use the number on your screen for the future calculation. You don't want to do any rounding, and you don't want to re-enter. That's a headache. Yeah. I'm going to report a number. This is approximately 978. That's pretty darn good. By the way, will you ever see a situation where you get a number of 1? What would a number of 1 mean? Every single point would have to be on the line. That's actually not realistic. That's really not even possible in real life. But if every single point is on the line, then you get a correlation of 1 or negative 1.
It makes sense though when you look at the line. Alright, they're pretty close.
They're very close. So we know that number is ridiculous. Do I still have to perform the experiment? Yes, because if the n is really small, Like I said, what if you threw 3 darts against the board and those 3 darts look like they pretty much lined up? By the way, you blindfold yourself, stand up close to the board and throw 3 darts. Is it reasonable those darts could more or less line up? Is that possible? Sure. And I would have a similar looking picture. Just because the darts lined up, that doesn't mean I have correlation. Oh, I only have 5 points. 5 points is not a lot of points. So that, that number being good is great, but if I had 50 points, then I'd be much more, confident. So the calculation for the Z, all right here. The Z calculation, this is our measured Z. It's actually kind of messy. It's the R on top over the square root of 1 minus R squared over N minus 2. Now, before we've been using N minus 1 all over the place. N minus 1 was always the degrees of freedom. Strangely enough, in regression, it's N minus 2. And here's why. If I give you exactly 2 points, didn't we say there can only be 1 line that passes through them? I can't deviate from that line until I give you a 3rd point, can I? So do you see why it's N minus 2? 2 points are absolutely always on the same line. It's not until you get to a 3rd point that you might be off the line. Oh, so the degrees of freedom are all but 2 points now. For the case, if I get all the way down to 3 points. Now, I put that in the formula. It says DF, degrees of freedom, is N minus 2. That's why this is N minus 2, not N minus 1. Now, I need to do this calculation, and I do not want to re-enter anything on my screen. You have a button on your calculator that says answer. You want to use that button. When you enter R squared. So here's what you're going to do. You have the R on your screen right now. Everybody got it? So you're going to go, you have the R on your screen, and you're going to now go divided by square root 1 minus, square root parentheses, because I need the whole thing in parentheses. But I need the numerator and the denominator. So believe it or not, I need 2 parentheses. I need parentheses around my numerator and then parentheses around my denominator and then closing the whole parentheses. So does everyone understand that I need, first of all, big parentheses so that I'm telling the calculator that it's all in the root? But because my numerator has 2 terms, I need parentheses around my numerator. I need parentheses around my denominator. So go slow. So your screen divided by square root. First open parentheses is the entire stuff under the root. Now I'm going to do the numerator. 1 minus answer key. Now your R should be back on the screen, but I want to square it. So now hit your squared button, whatever your squared button looks like. Okay, on mine it's an X squared. Some of you it's a hat squared. Okay, everybody, so far so good? First close. Now I finished my numerator. Now what do I got to do? I need to divide it by what? Divided by what in this problem? How many points do we have? 5. So what's N minus 2? 3. So divided by 3. Because I don't actually need to put parentheses around 3, but I need to put parentheses now around that because now I've finished everything under the root. So you with me? So I'll do that on my calculator. Divided by square root. You got 8.2. Anybody else get 8.2? No, yes, maybe? I got the same thing. So again, the whole mind thing is basically switched over to you, Andrew. I got approximately 8.20. Okay. Did you get that, Junior? This is why the parentheses are so critical. Do you know why you love your answer key? Because you don't want to have to write down this whole thing and then re-enter this whole thing. And you never want to use a rounded off answer in your calculation. I want to use the whole thing, but I don't want to re-enter it. That's why answer. Now, Salvador, did you get 8.2? Did you re-enter something? Maybe your R was slightly different. It should be 8.2. Yeah. Andrew, why don't you show how to use a calculator? Did you get that? That's a Z value. Would you say that's kind of extreme? Now, okay, remember, what does our picture look like? Here's our picture. What are we going to do? We're going to reject at this end. We're going to reject at this end. Where are we? We're about 5 miles that way. So we didn't just fall in the shark-infested lava. We were rocket launched into the other end of the shark-infested lava country. So does that make your conclusion rather simple?
Yeah.
Reject the null or fail to reject the null?
Yeah. No. Reject it.
You're in the shark-infested lava like 1,000 miles into the shark-infested lava. I'm pretty sure you want to reject the null.
Reject it and your piece.
In other words, is this a close call? This is not a close call. By the way, we love it in real life when it's not a close call. We don't want to have to make decisions. We want it to be obvious. We are clearly going to reject the null. We were a mile out there. We said we'll reject the null if we exceed 1.96. I think we exceeded it and then some. So our conclusion is reject null hypothesis. And again, a lot of you forgot to do this on the exam. You haven't stated the conclusion yet. The conclusion is not reject or fail to reject. The conclusion is the next thing you say. Remember, I always said it this way. What is the truth? You're going to have your press conference later on today. Folks, at the end of the trial, we've failed to reject the null. See ya. So therefore, what's going to happen? We've rejected the null hypothesis. So what's going to happen? Does everybody understand? When you are rejecting or failing to reject your conclusion, absolutely always your conclusion has to do with your alternative. When you reject the null, you say the conclusion is the truth. I'm sorry, the alternative is the truth. When you fail to reject the null, you're saying more often than not, there wasn't enough evidence to say this was the truth. And occasionally you'll say, no, actually, this is the truth. Now, you rejected the null. Therefore, what's the truth? In words, what does this say? There is correlation. Does that make sense? Rho equaling 0 means no correlation. No, because you're on trial. You're either guilty or not guilty. You're not on trial for innocence. There's no such thing. Guilty means you rejected the null. Not guilty means you failed to reject it. Not guilty does not mean innocent. Now, could not guilty mean innocent? It could, but it doesn't automatically. Not guilty usually means there wasn't enough evidence to find you guilty. So when you fail to reject the null, you're saying there wasn't enough evidence to conclude the alternative. Now, occasionally the evidence is so overwhelming, you'll say, no, I believe the null actually is the truth. Not in this case. And we landed in the shark-infested lava like 1,000 miles out there, where it's really hot lava, way hotter than the lava up close. You know, that lava is just regular lava. Yeah, the other stuff's like superheated lava. Okay, so we rejected the null. There is correlation. In fact, pretty darn strong correlation. Now, let's back up a step. What if these points were much further away? Then this number would be much smaller, agreed? But when that number is much smaller, this number would be much smaller, and it would start closing in on 1.96. Is there a point when my points are just too far away from the line that this number is now smaller than 1.96? Yes. In which case I'd say, fail to reject the null. There's not enough evidence to conclude there's actually correlation. Yeah, it was an illusion. That's literally what that would mean. Does that make sense to you guys? So the calculations are tedious. They're not hard. They're tedious. So the rule of thumb is, in the order I just did things, find the sum of the x's, the sum of the y's, the sum of the x squared, the sum of the y squared, the sum of the xy's. That's your quick calculations. Then those go into this. Those are the big numbers. And just so you know, when we find the line of best fit next day, the line of best fit is going to use all of these numbers again. So next day, when we actually calculate what's the equation of my perfect line, it's going to involve all of these guys again, okay? But once I do that, now I can calculate my correlation coefficient is what it's called. And it's got to be between -1 and 1. Well, how in the world could my correlation coefficient ever be negative? Because my numerator was the sum of the xy's. Oh, when I did the sum of the xy's, I multiplied the x times the y coordinate. What if all of my xy's were opposite signs? You know, one positive, one negative. Then wouldn't the sum of the xy's be negative? In other words, my correlation coefficient can be negative if the line is going downhill. And that's not actually very hard to get, okay? All right, what I want to do now.
You didn't finish it.
Oh, thank you, Andrea. Projecting all.
Negative 10 points right there.
There is correlation. Your alternative hypothesis, rho equaling 0 means there is no correlation. So rho not being 0 means there is correlation. Don't say reject the null, rho is not 0. No, you always use words. Use words. There is correlation, right? Isaiah is a better free throw shooter than Sarah. Not P1 is greater than P2. That sounds too mathy, doesn't it? Sometimes we give our conclusion and we're using numbers. But the point was, you're saying, gee, is this restaurant slow or is it not slow? My conclusion is that the P is greater. No, my conclusion is the restaurant is slow or the restaurant is not slow. The words of your conclusion should kind of match the words of the problem. We're trying to determine if there's correlation. Hey, there's correlation.
For these questions, like the last unit or the last lesson, we used to look for p-values. Are you going to make us do that?
Not in this case. By the way, you'd have stuff with 8.2, wouldn't you? What's the probability of being bigger than 8.2? It'd actually be something like 0. No, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, but there'd be a lot of zeros. You know, maybe a million zeros or something. It'd be really small.
So does that mean that like this would be like almost impossible? Or like, is it possible that correlation is more probable than other ways in scores?
Correlations most of the time are pretty simple conclusions, because what ends up happening, if there's correlation, your z-scores are usually really, really big. And is a really big z-score good? Yes, because if I'm going to reject for really big or really negative, and my outcomes are really big, it makes my conclusions easy. I'm way out there in rejection land. Now, if I just randomly gave you points that literally look like they're kind of around a circle, when we do the calculation for R, it's going to be really small, positively or negatively. And therefore, this would produce a ridiculously small z, in which case you'd say, no, there's no correlation. Fail to reject, there's no correlation. And that's the real life. We're keeping it simple, okay? So what I want to do now, I want to take the problem quiz and have you guys test it. You like it when you do that? You should.
I was going to say we should take a little 5-minute break.
Yeah, let's go take a minute for this to warm up anyway.
It has a lot of parts.
It's, like I said before, it's tedious calculation. The only thing you're given is a set of ordered pairs. You're doing lots of little calculations along the way for a bunch of little ordered pairs. Now, I don't have a classroom at all where these things work well. They spent $1 bazillion on the building and they bought the absolute cheapest equipment you could possibly find. The computers were from Radio Shack. I'm not joking. There we go. The sound systems all completely failed within the first semester we were here. That's why nobody uses the microphones anymore. Uh-oh, what's on my screen? Hang on a minute. I had this up. Okay, well, let's see.
There you go.
Is it up now? Okay. It disappeared for a little bit. All right. So I have 10 ordered pairs. So you're going to do exactly the same thing we just did a moment ago. Let me go ahead and give the lights. You have 10 ordered pairs. It's the same problem exactly. All right. So you can find, I'm asking for these three things here, but you can't find any of them until you first find what? The sum of the x's, sum of the y's, sum of the x, y's, you know, x bar, y. You got to find all those little pieces first.
So it won't be a question. It'll just be,
Well, I'm asking you to do the, I'm kind of doing it in reverse order. I'm asking you to do the calculations first and now state the hypothesis. Well, we're getting, like we just did, we're getting the calculation out of the way.
you said that you have to calculate the sum of the scores.
And I'm asking for all of those things, but before you do it, you got to first add up the x's, add up the y's.
Yeah, my question is, you won't ask for, like, up there.
Am I going to ask these separately?
Yeah.
No, I'm actually just jumping to here. So you can't do these until you do these, obviously. Because if you look at the formulas, do I have it on here? Yeah, oh, I have it right here. I'm telling you what that's to say. Oh, okay, I have to actually do that. I have to do that. I have to do that. I'm asking for these calculations, which means you got to do all the little bit.
And it's always going to be these five.
Yes. And then X bar and then Y bar. So there's technically 7 things. Because X bar, Y bar also shows up. You have to calculate n? No. I told you what n was, right? I said there are 10 data points. So n is 10. And the problem that I did at first, I used 5 data points. Now I'm giving you 10. Okay? Everybody cool? All right, so let's take a minute. This is exactly the same question. I just gave you more data points. So go slow. And as always, I would do every calculation 2 times. And it's just wise. We don't have to talk to each other because this is not conceptual in any way. This is just do it. Does anybody else have a quiz 22 they're going to give me?
Yeah. I don't know. I was going to do it.
You do have a.
You're asking a question?
Oh, yeah.
Like you're using.
Because like I redid the because I know that I put 80% on multiple.
Is there a decimal in there? 20. That's not that big. That's too big. That just does that make it easier to make a conclusion?
Yeah.
Yeah, you're not miles out of the charting test a lot, but you're remember it's not a question of degree. So did one die or did not one die? So therefore, you're telling me why you that's not a conclusion, that's why you reject it. No. The conclusion basically is to say the words that you believe that's true. That's the one you keep reading out. This has nothing to do with it. That's not a conclusion. That's a comparing numbers. That's why I rejected it. That's why I rejected it. So at the end, when you're giving a press conference and you're saying, is he guilty or is he not guilty? Well, the Z value is bigger than the criteria for rejection. But they still don't know he's guilty or not guilty. The conclusion should be in words. Not because that you never need to say why you rejected it because that would be that. That's the one you can reject. It's an absolute rejected it if it wasn't being rejected. So you don't need to say I rejected it. Or you can just say this is bigger than this, about this. What are you testing? Whether Sarah is recognized or not? Would that make more sense to the You're telling me why you rejected it. If you're telling no, you rejected the hypothesis. Not because. There's never a because is implied. There's only one reason you can reject it, and it's because of that.
You don't really need to restate that, that's kind of implied. Or you can make that the first thing that Sarah, because that either she wants or she doesn't. But you're giving a press conference at the end of the day, right? All the media is standing on taking pictures, and you get up there and say, "We rejected the null," and you walk away. That's what you're doing. You're rejecting the null and walking away, and they're left going, so is she better? Remember, there's only two possible answers. She's better, or there's not enough evidence to say she's better.
I forgot my
Does
glasses.
that make sense?
Yeah.
That's the thing you've been leaving out. You've not been telling me. The conclusion is what's the truth? Based on my experiment, based on my hypothesis. So you're always, I rejected the null or I failed to reject the null. And now what is the truth? There's always those two pieces. The reject and fail to reject is the easiest part. I have a line in the sand, did I cross it or did I not cross it? But then again, now on the fail to reject, you have the license to say, you know what, I'm just considering none of that is the alternative. Or the evidence is pretty overwhelming that the null was actually true. That is a possible answer. Sometimes that happens. You know, what if this was negative? In other words, what if Isaiah outshot Sarah? Then you would say, not only is Sarah not a better shooter, Isaiah is actually better. That's, you use this all the time in science class. You use it before. And the conclusions, really want the conclusions to be clear. You don't want them to be nebulous. We don't like close calls. We want black and white. We want gray over the field questions.
Yeah.
You know, it's almost like the idea I can do the experiment again and get a different conclusion if it's too gray. I really want it to be. I love rejecting it because it's black and white. Failing to reject always leaves a lot of wiggle room.
Yeah.
But that's more often than not what happens.
I forgot my glasses. I was gonna bring them and I forgot them.
Right?
No.
Right. What you mean the calculators? That seems kind of overkill. You're adding up all the X values.
I know, but it helps me. Like, it helps me visually see what I'm doing, because if not,
Okay.
I can't go look back and understand what I did, you know?
Okay. So we're getting somewhere? I don't expect you to be done. I don't want you to be done yet. I want you to go and do the stuff. You already got the numbers? Yeah.
I think.
I'm not saying wrong. Did you do everything twice?
Yeah.
By the way, I'm pretty good at this stuff. And I'm smart enough to know to always do it twice. And I've done this stuff on a computer using powerful software. I still do it twice because there's always a possibility of miss. And it's right.
I did it twice, and then I also.
Well, the other nice thing is you have a calculator where you can see. You may not actually have to do it twice. You just double check your screen.
Yeah.
That's kind of the overall, isn't it? The problem though is that you have to scroll. You can't see everything at once. When you're doing a problem on a computer, you can often see everything at once. That's a good thing. Yes.
For this one, I don't need to put
Hold on a minute. I'm gonna pause the recording for a minute because we don't need to. While you guys are calculating, we don't really need to record. Again, just remember, the sum of the x's, pretty simple. The sum of the y's, pretty simple. The sum of the x squareds, 0 squared plus 1 squared plus 2 squared, go a little slower. The sum of the y squareds, 46 squared plus 52 squared plus 56 squared, go a little slower, always double check. And then the sum of the xy's, that product plus that product plus that product, all the way down the line. I have to have those before I can do anything. There are 10 data points. So x bar, of course, would be the sum of the x's over n. Y bar would be the sum of the y's over n. So there are 7 values that you have to calculate before you can find these. So always double check them on your calculator. Do it twice. Or if you're lucky, you have a calculator where you can see all the input and it's pretty simple. You can just check the inputs. Once you do that, the calculations for number 1, the rest of the calculations, SSX, SSY, and SSXY are automatic. Then I take those values and I calculate the R. And then down number 4, I take those values and calculate the Z.
Okay, I'm going to check this page. Okay. Wait, that's not that big though. Did I do something wrong?
It's like a healthier energy drink, I guess. It's
Healthier, does that mean less terrible?
It's got,
Everything back
no,
without moderation.
I don't know, but it says it gets the caffeine from tea. I don't know how accurate that is, but it definitely helps me feel better about drinking energy.
Not recommended for people with caffeine sensitive.
Sometimes people's insulin increases when they drink caffeine. Yeah, I know.
Really?
But only with like diabetic individuals. Sucralose is an artificial sweetener that needs very minimal amounts, like insulin over.
Not like that's what they, what's the deal?
Oh, one minute is really old. Stevia, I think.
Stevia? What did you say?
Stevia?
No, what? I said, no, I said aspartame, you said something.
Aspartame?
Aspartame.
That's how I pronounce it.
Oh. I think you're throwing an extra vowel.
Yeah.
That's that was the first one. What was that?
So what this,
It has a name, I think. The generic, not sweet, Nutrasweet. Have you heard of Nutrasweet?
No.
Oh, that's the sweetener that was added in the 80s and 90s and 2000s. That's aspartame. No, that's not the bad one. Aspartame is strange enough. It was tested for 10 years. It came out. It was supposed to be the most healthy alternative to sugar, and then they found out. No, they didn't check this when they had their thousands of people who tested and it was safe. But if the soda is in between temperature, it breaks down. And that can affect certain people. And so we had deaths from people drinking it because it broke. And they didn't know that. They didn't test for it. It's like, oh my God, you can't. So in other words, if you have your soda, cool. If it got warm, you're probably fine. But there were individuals, very rare, but there were individuals with that. Yeah, and as much as they tested it, that was not some, I don't know why wouldn't you test it? But, or maybe the whole test individuals won't detect it. Because I didn't study for years and years and years, and it still had a flaw. Now, it was still probably the safest alternative. Now, there have been many since then. Yeah, I believe that what I said, Nutrasweet is. So you buy a soda and it's say, sweetened with Nutrasweet. People feel very safe. That's aspartame, I think. Yeah. You rather than re-enter the part, yeah, you can do like that. Okay. Yeah, you can do like that. I don't. You already had on the screen.
I didn't re-enter it, but this was
yeah. If you could graph these, if you have the ability on your calculator to graph these, you'd see they're pretty. They look that line, and that's a good thing.
Can you check this? See if that's right.
Well, if those are right, that's kind of hard to mess that up. And that part's pretty simple, right? 50 divided by 10.
What about this one? Did I write that right?
Well, let's see. You've got x minus 10 times yes. And that minus yes. Yeah. You have to have a little bit of faith.
I don't have that.
When you're using a formula, as long as you follow the formula, you're probably okay. That's why I say double check that you're actually doing the formula correctly. Okay. So we lost Junior. I think he was done. he reached saturation. Is that what you're saying?
His brain's done.
They asked me to teach this class in the fall again, and I said, no. Not at 7:15.
The only reason why I'm here at this time is because I didn't check the time.
Okay, pause. This is